Hey everyone. On today's AP Stats, we're going to play the fun game of Can You Guess My IQ? Which is going to take a further look at residuals and what they actually mean for the least squares regression line. This game is kind of actually more along the lines of my counselor did what? What did my counselor do? So without talking too much about the counseling department, let's go take a look at what we have in store here. Remember, this is completely fictional. So as part of a transcript for our school, the counselors have decided to include IQ score in addition to GPA. Now, they would never actually do that, but this is fictional, of course. So the question is, if we know someone's GPA, can we predict their IQ? Maybe. I don't know. So we got 5 students who requested that their counselors update their transcripts for them. We've got Adam, Bernard, Christy, Deja, and Eldon. Their IQ scores are 110, 85, 120, 95, and 105. But they have been all mixed up, and the counselors, that poor counseling department in this fictional school, doesn't know which IQ score goes with which student. So we've got a bunch of guidance counselors, and they're forced to predict the IQ for each student. Each counselor will take a different approach. So let's talk about counselor 1, the new guy. So the new guy is so nervous about being wrong that he wants to play it safe. So I'm going to underline that. We want to play it safe and minimize his error. So what he decides to do is to find the average IQ and use that IQ prediction for all 5 of the students. Well, that's not hard to do. We're just going to take all of the IQ scores, 110 plus 85 plus 120 plus 95 plus 105, and we're going to divide that by 5, and what we actually get is 103. New guy says, dude, I don't know what your IQs are, but I know that the average IQ is 103. So let's just say that everybody's IQ is average 103. And that sounds kind of crazy, but we kind of do that all the time when you think about it. We use the average to make a prediction about things. And it's not really a crazy thing to do. How about the veteran? Counselor 2, the veteran, notices an equation on the board of the AP Stats room, of course. And the equation is IQ is equal to 16 multiplied by the GPA plus 57.3. So obviously not a great stats department because they wrote that backwards. It should be 57.3 plus 16 times GPA. That's a backwards equation. And she realizes that she can use that GPA to make better predictions. So we're going to go one by one with each of the students and use that equation to estimate IQ. So here's Adam. We've got IQ equals 57.3 plus 16 times 1.8. That gives us 86.1. And we'll do that for the next student, Bernard. And then we'll just continue. Made a little bit of a mistake on that very last one. Hopefully that's not going to confuse you too much. So here are the predicted IQs for counselor number 2. Now let's take a look at counselor number 3. Counselor number 3 is who we call the truth seeker and does probably the most sensible thing, and is going to pull all the 5 students out of class and finds out what their actual GPA or their actual IQ was, straight from, as it were, the horse's mouth. So Adam actually has an IQ of 85.1. Bernard's IQ was actually 95, etc., etc. And so let's see which counselor made better predictions. Counselor 1. Counselor 1 predicted that everybody's IQ was 103. And if we calculated error, which is basically the same thing as residual, actual minus predicted, 85 minus 103, that's negative 18. 95 minus 103, negative 8. 110 minus 103, that's 7. 105 minus 103, that's 2. And then 120 minus 103, well, that's going to be 17. Now, if I added all of those values together right now, if I added all those errors, I would actually get a value of 0. So we're going to do the official stats route here and square each one of these errors and add that together. So let's square them all. Negative 18 squared is 324. Negative 8 squared is 64. 7 squared is 49. 2 squared is 4. And 17 squared is 289. Now, to figure out an expression that gives me the total amount of error along this using the predicted IQ, I can just add all of that together. And if I add those square errors together, I get 730. Is that good? Is that bad? Well, I don't really know unless I have something to compare it to. So let's compare it to Counselor 2, the veteran. Now, the veteran used the line of best fit for every prediction. And as a reminder, that line of best fit was the predicted IQ equals 57.3 plus 16 multiplied by the GPA. So let's get the predicted scores here. And I'm not going to do them one by one. We'll put the predicted scores here. And then just like for Counselor 1, we're going to subtract the actual minus predicted. That's going to give us an error. Now already you can see already that the errors for the veteran using the least squares regression line, that's a lot less than the errors using just the average. We're going to square the errors so we can compare the squares. Look how much smaller those are than their corresponding values for the new guy. Squared errors here. The biggest squared error is 4489, while the biggest squared error here, that's 324. So it's a huge improvement. If I added them together, I get 89.89. Huge, much better than 730, don't you think? So who did better? Well, we would say that the veteran did better because the sum of square errors for her predictions, assuming it's a she, is less than the sum of the square errors for his prediction, 730, assuming it's a he. So Counselor 1, sum of square errors, and Counselor 2, sum of square errors, 730 and 89.89. And then the next thing here is going to be calculate the percent improvement. So how do we calculate percent improvement? Well, percent improvement is the amount of change divided by the original amount. For us, that's 730 minus 89.89. That's going to be our amount of change divided by what we started with, which was 730. That's going to be 0.877. We could also find each counselor's typical error. So we're going to use algebra to turn the sum of squared errors into an average error. So to find the average error, we're just going to, for Counselor 2, take the sum of the squared errors, divide that by how many students we had, and then square root that result. Oops, we had 5 students. Now if I square root that, I should get, now that gets us 4.24 after we take our square root. Now, the next thing we're going to do here is we're going to get this stuff from our calculator. Okay, so let's go ahead and grab our TI calculator. We'll head over to Stat Edit, clear everything out, and then we'll enter in the GPAs, put in the IQs, go to the home screen, and calculate that least squares regression line. Stat calc linear regression a plus bx, that's number 8. Our x list was an L1, our y list was an L2. We have no frequency list, and just get in the habit of putting that into these, storing the regression into y1. And let's calculate. All right, look at what we have here. We've got a linear regression, clearly, and we've got an r squared of 0.877 and an r of 0.936. Putting in our values for r and r squared, that's interesting. Take a look. I mean, r squared and r, that 877, well, that's the same number that we found up over here, the percent change. So r squared is just a percent improvement of using the least squares regression line over the averages. So we can kind of say that the r squared says that we have an 87.7% improvement on the residuals, or we should say reduction of residuals, when we use that LSRL. Now the last one here is the value of S. Now, but what about this S? Okay, so S is actually going to be the standard deviation of the residuals. Now you might think that we could just plop 4.24 in there because that's what we got here, but that's actually incorrect. Or to be more precise, that 4.24 represents a standard deviation of the residuals if there were only 5 numbers in the population, or 5 IQ scores in the population. In order to get the standard deviation that we're interested in, we have to treat these 5 scores as if it was a sample. And to do that, instead of dividing 89.89 by 5, we have to divide 89.89 by 5 minus 2. And what that does is it introduces a little bit of error. It makes that standard deviation measurement a little bit bigger than that 4.24. And if we do 89.89 divided by 3 and then we square root it, we get 5.473. And this 5.473, that's our standard deviation of residuals. Now, that's quite a lot of calculation that we did there. I don't blame you if this is completely spinning your head around and around. We do try to make it as easy as possible. So let's get these ideas here, okay? So learning target 1, that's going to be S. S is a standard deviation of the residuals. But remember, for your standard deviation of the residuals, you have to square root r squared divided by n minus 2. Now that n minus 2 is going to definitely play into second semester. But for now, we'll just take it the way it is. Now, the interpretation for S, that's going to be the actual response value is about typically S units away from the value predicted from the explanatory variable. It tells you basically a typical error of the prediction. R squared, however, that has a special, and if I may say so, it's a pretty badass name. It's called the coefficient of determination. And the interpretation here is about R% of the variation in that response variable is going to be accounted for by a least squares regression line with the explanatory variable. And if you remember what we said before, it is kind of like a percent reduction in the residuals. So if you keep it along that line, it kind of makes more sense. But this interpretation is the one that we're going to have to use over and over again. In our Check Your Understanding, we have the same data, I believe, about the 9th grade students on that backpacking trip. The least squares regression line we calculated last time. Let's go ahead and grab that. And from before, we got that the predicted backpack weight was 16.26 plus 0.091 multiplied by body weight. The next thing here to do is to find and interpret S. Going back to our calculator, we're going to make sure we have those numbers into the list 1 and list 2. And then from the home screen, we'll calculate that linear regression. And the reason we're doing this is we need to get that value of R squared. Let's get our value of R squared. Cool. Our R squared is 0.631. Now to find our value of S, we're going to have to figure out, well, where did that value of S came from? Looking back, it was this 89.89 divided by the number of coordinate pairs minus 2. Well, where did 89.89 come from? 89.89 came from this sum of all of the squared errors using the regression line. So what it was the actual minus the predicted squared, and then all of those squares added together. So to find that number for us, we're going to have to add together basically that same quantity. We can do that in list 1, or I think we've used list 1 and list 2. So we can do that in list 3. So we can figure out the square of the actual minus the predicted, sum of the squared residuals. So where were the actual values? Well, actually, before we start, make sure that you have L3 highlighted here. And the actual values were in list 2. Minus. Now the predicted values, you probably noticed that I stored the regression line in Y1. So we'll go over and we'll put a Y1 here. And into Y1, we'll put all the X coordinates, which were in L1. And then we'll square that. So we're doing all the squares of the actual minus predicted. Cool. And that gets me to L3 would be the squared residuals. And coming to think of it, actually, we could have done this a lot easier is if we just did the square of all the residuals. So if we go to the residual list, and then we square it, yeah, that'll give me the exact same list. So now we have the squared residuals. All we need to do is add everything together from list 3. So from the home screen, we would go to List, Math, Sum, and we're going to add sum of list 3. And that gets me 30.905. And just thinking about this, you could probably even make this easier is if we go to Math, Sum, And if we sum the residual squares here, we might save ourselves an extra step. And yeah, that gives me the exact same thing. So that's the sum of the squared residuals, 30.905. Okay, back to our notes here. We've got s is equal to the square root of SSR over n minus 2. So we've got the square root of 30.905 divided by 8 minus 2. Back on the calculator, we can do the square root. And we'll do a fraction bar. We'll call up the 30.092905, and then we'll divide that by 8 minus 2, and that should give us our s, which is 2.27. Okay, so that is a really lengthy calculation, well, depending on your commitment to it. And I got to assure you that this isn't something that gets done often in AP Stats. More often, you will get a value for s, and you will have to interpret that. Here's our sentence frame. The actual response variable, which is backpack weight, is typically about 2.27 pounds away from the amount predicted by the LSRL with the explanatory variable, which is body weight. Okay, well, that is our interpretation for s. Earlier, we found the value for r squared, and now we can interpret that. Let's grab the sentence frame for r squared. We have about r squared. Well, r squared is 0.683 of the variation in the response variable, which was backpack weight, is accounted for by the LSRL with our explanatory variable, which is body weight. So that kind of does it here. I know we got pretty mathy there in the middle, actually near the end there. Hopefully the calculator tricks will help you. Rewind this, watch it over and over again, and I'm sure you'll find an easy way to calculate s whenever you need to. So that's our lesson for today. Have a good one, and we'll see you on our next one.